Hello everybody, welcome. This is paper 2 from May 2023. Let's have a look through it and see what we can do. Okay. Question 1, 17 marks. The diagram shows points in a park viewed from above at a specific moment in time. The distance between two trees at points A and B is 6.36 meters. Odette is playing football in the park and is standing at point O, such that AOB is 10 degrees, OA is 25.9, and OAB is obtuse. That's saying it's greater than 90 degrees. First question, part A, they're asking us to calculate the size of ABO. So ABO, they're asking us to find this value right here, which we can call theta. So in the realm of non-right angle trigonometry, we have three formulas essentially that we can draw on: sine rule, cosine rule, or the area of a triangle. Sine rule is generally going to be the most straightforward and easiest to apply. So let's go ahead and see if we can use the sine rule, and if not, then we might need to use cosine, and so on. So to use the sine rule, we are looking for two pairs of angles, an angle and its opposite side length, and another pair where we have an angle and its opposite side length. So here we know we have one angle and its opposite side length, and we actually have this angle that we're looking for is also opposite to a side length that we know. So we know 3 out of the 4 unknowns, so we should be able to apply the sine rule here. Alright, let's go ahead and label our side lengths. So if this is A, let's go ahead and label this A. This isn't entirely necessary, but it's good practice, I suppose. So this would be A, and this would be B, and then this would be O. Sine rule is in the formula booklet, but I'll go ahead and write it here. So we have sine B, in this case, over B, and we're going to have sine O over O. So we don't know sine B. In this case, we actually called it theta, so let's write it sine theta. And it's across from this side length of 25.9. And we do know sine O. In this case, it's 10 degrees. And we do know its opposite side length, and that's 6.36. Okay, you can manipulate this with a little algebra, but we can also, if you're not exactly comfortable with that, we can also just end solve for theta. All right, so let's go to the calculator and work that out. Make sure you're in degrees, of course. Everything in an AISL paper is going to be in degrees. So let's go to the calculator screen, algebra, numerical solve, and let's type this in. So we have, actually first we have to write a fraction. So one fraction, and we have sine, let's call it x, over 25.9, and this is equal to, setting up another fraction, sine 10 over 6.36, and we're asking the calculator to solve for x. Right, there we have it. So let's go back to the document, and we found that theta, let's change the color, theta is equal to 45.0037, or to 3 sig figs, 45 degrees. Just to be clear, I guess, they're asking us for ABO, so I suppose we can also write this as angle ABO is equal to 45 degrees. Not bad for a 3-mark question. Calculate the area of a triangle. Okay, we're still in the realm of right angle trig. I'm going to clear some space, what we've found and what is essential. So now we have, this is 45 degrees. The area of a triangle, once again, this is given in our formula booklet. Let's actually just go find it this time. Not a bad idea to get familiar with the formula booklet. So here we are. Here is our formula booklet. This is going to be under Geometry and Trigonometry, Topic 3. And here we have it, 3.2 right at the bottom. Area is equal to half AB sine C. So let's go back. So what do we know? We know that the area, let's just give a mark. Area is equal to half let's write it out not to confuse variables, is half AB sine C. So what is going on here? To calculate the area of any given triangle, let's draw one here, I suppose. Some non-right angle triangle, something like that. If we have, let's say, one angle and two side lengths. So if we have, let's say this is 12 and 15, if we have an angle, an included angle, and two side lengths, then we can solve. So if these are two legs of a triangle, we need the angle between. So we call this an included angle and two side lengths. So the angle between two known side lengths. And we can ask ourselves, do we have that situation here? Okay. So to find the area of a triangle, we don't know this side length. It's unknown. The side length OB. We could find it by cosine law, but we do know this side length and we do know this side length. And generally speaking, it's easier to find an angle. In this case, if we already know 2 out of 3, and it might be easier in this case to find the included angle. So let's go ahead and call this, it actually already is OAB. So let's go ahead and find out OAB, angle OAB. And what is angle OAB going to be equal to? How can we write this out? We know that 10 degrees plus 45 degrees plus OAB is going to equal 180 degrees. So maybe that's the method that we should use. So OAB plus 10 degrees plus 45 degrees is going to be equal to 180. And if you want, instead of writing OAB, you can just call it x. So let's go work that out. You can end solve this, or to be honest, actually you wouldn't end solve this. You would probably just use a little algebra, I suppose. So essentially, we have angle OAB is equal to 180 minus 55, or we could say that OAB is equal to 125 degrees. So if we know that this is equal to 125 degrees, we found the included angle. Now we already know these two side lengths, this 25.9 and this 6.36. So let's go ahead and use our area formula. Once again, area is equal to half AB sine C. So area is equal to 1/2. Side length 1 is 25.9. Side length 2 is 6.36. And the included angle, the angle between these two side lengths, is sine 125. Okay, let's go work that out and return to the calculator. All right, so let's write 0.5 times 25.9 times 6.36 times sine 125. Sine 125. Okay. So this is the area of our triangle. The area is equal to, let's go back to the document. Actually just reading here, 67.467. To 3 sig figs, this would be 67.5. So I'm going to write it all out. 67.467, which we would then round to 67.5. Okay. Not bad so far. Not bad so far. Units, I think we're talking about meters. Meters squared. Okay. Let's continue on. Odette's friend Camille is standing at point K. So here's Camille. Such that he is 12 meters from A, and KAB is 45 degrees. Calculate Camille's distance from B. So sometimes you do enough IB questions, and not all of them, but potentially there are some that are straightforward, and they become almost somewhat formulaic. So when we're talking about non-right angle triangles, we have our 3 formulas that we talked about: the sine rule, the area of a triangle, and then we also have the cosine rule. it'd be unlikely within a paper 2 question, a long form question, for them to say use the sine rule twice, because they've already tested that skill. So what might be coming next, just already kind of making a prediction, potentially the cosine rule. So calculate Camille's distance from B. Camille's distance from B. So here is Camille at point K. This is what we're trying to find. We're trying to find this distance right here. Let's call it, we already used A before, but let's just call this X then. All right, so what do we have? We can't, or can we use the sine rule? In this case, we need an angle opposite side length, but we don't have this angle right here at K, and we don't have this angle here, so that's not going to work. But we can use, in this case, the cosine rule. Cosine rule will work when we have 3 known side lengths, or let's say a situation where we have 1, 2, 3 side lengths and an angle that is opposite the side length that we are concerned with. So cosine rule is actually kind of similar to the Pythagorean theorem. It's pretty lengthy. It's in your formula booklet, of course, under trigonometry. Once again, here it is, 3.2. And it looks a lot like the Pythagorean theorem. So let's go back. So what is it? We have, I'm going to write it out in a slightly different form. A squared is equal to b squared plus c squared minus 2bc cos a. And we see this large A maps up with this A at the beginning. And this large capital letter refers to the angle, and this refers to the opposite side length. So the side length that is opposite to the angle that we are concerned with, in this case, angle A. So here's our cosine rule. Let's substitute for our unknown. We don't actually know x squared right here. We don't actually know x squared. So let's write that in, x squared. But we do know the other 2 side lengths. We do know this is 6.36 squared, and we do know this other side length of 12 squared. 12 squared minus 2, 6.36 times 12, and then we have cos, and thankfully we do have this angle which is opposite this side length right here. So we have cos 45. Okay, that's it. Now, I mean, we can just type this all into our calculator and then essentially take the square root of all of this, but we can also n-solve this. I'm actually going to work this out by finding the value of everything on the right side and then taking the square root. So let's go back to the calculator here. All right. Let's clear a page actually and get to it. So 6.36 squared plus 12 squared minus 6.36. Oops, sorry, minus 2 times 6.36 times 12 times cos 45. All right, and it looks like I might have, oh, that looks good. Right, and it's 104.264. Let's go ahead and take the square root of 104. Okay, so there's some more decimals behind it. At 104.26. So we want to take the square root of all of that. Essentially, you could have set it up with an n-solve, just writing x squared is equal to all of this business, but this is the same way as well. So 10.211. Okay, going back to the document. Therefore, x is equal to 10.211, or to 3 sig figs, x is equal to 10.2. That's Camille's distance from B. Okay. Keeping on. xy, let's see what that is. xy xy is a semicircular path in the park with center A, such that KAY is 45 degrees. Camille is standing on the path, so here's Camille, and Odette's football is at point X. This is shown in the diagram below. Okay, so here's a football, here's Odette, here's Camille, and there's this semicircular path right here. Okay, the length KX is equal to 22.2. So KX is equal to 22.2. KOX is equal to 53.8. And OKX is equal to 51.1 degrees. Okay, so it's kind of interesting they're not actually giving this information on the diagram itself. So first things, I mean, when you get a geometry question, best idea is generally to go ahead and actually label this, label your diagram. Okay, so KX, let's go ahead and draw a line. It's not a bad idea to bring a ruler to the exams. I never did, but actually looking back, it probably would have been a good idea. KOX is equal to 53.8, so let's go ahead and draw that information. KOX, so this is KOX right here. Let's go ahead and label that, and it is equal to 53.8 degrees. And OKX is equal to 51.1. This is equal to 51.1 degrees. Okay, not bad. Find out, or find whether Odette or Camille is closer to the football. Whether Odette or Camille is closer to the football. So let's actually just label this. So opposite O is this O right here, and opposite K is this K right here. And so the question is, we want to see is K greater than O, or is O greater than K? Interesting. How can we do this? I think even before approaching, given that we have 1 and 2 side lengths, not a bad idea to find the third, because it'll just often sketching a diagram or sketching a question and then putting all the information that's known is a helpful way to see what kind of possible approaches are open. So let's find this theta value right here at this vertice, OXK, I guess. Let's call it, just for the time being, y, just for simplicity's sake. So what do we know? We know that y plus 51.1 plus 53.8 is equal to 180. I'll actually just do this one on the calculator that I have beside me. 180 minus 51.1 minus 53.8. And so y is equal to 75.1, what we've called y. 75.1. So let's go ahead and actually just erase that and put that value in. 75.1 degrees. Okay, we know 3 angles, and we have an opposite side length, so it looks like sine rule is actually going to be okay. And let's go ahead and do that. So let's find K. We have side length, an angle and its opposite side length, and we have an angle and its opposite side length. A little peculiar that they're asking us to use the sine rule once again. It could be the question, the skill that they're kind of testing here is being able to construct a diagram based on a set of, or some information. So let's go and use the sine rule once again. Let's solve for K first. Okay, so K over sine K is equal to, this is probably a big K, sine K is equal to O over sine O, and we have, again, angle opposite side length, we have 2 pairs, and we should be able to use the sine rule. So what do we have? K over sine 51.1 is equal to 22 22.2 over sine 53.8. Okay, let's go ahead and put this into our calculator. Sorry, when I made a new document, actually, calculator went back to radian by default. So let's go document settings, and let's make sure we're back in degrees. Okay. Let's go ahead, menu, actually sorry, what are we doing? Not menu. Algebra, numerical solve. Again, you can do this with some algebra, but we can also end solve if we need, or if you need, or if you're more comfortable with it, either way. Okay, let's put in k. Let's actually use these values. Sine 51.1, trig sine 51.1 equal to, and then we have another fraction right here, 22.2 over trig sine 53.8. 53.8. Too few arguments. Okay, I'm sorry. Need to tell the calculator what to solve for. 21.41. 21.41. Okay, so let's go back to the document. K is equal to 21.41 or, to 3 sig figs, 21.4. So if this is 21.4, that's how far Odette is away from the basketball, or the football. And Camille is 22 meters away. So I keep interchanging. 22 meters, not feet. So find whether Odette or Camille is closer to the football. What can we say? 21.4 is less than 22.2. And if you want to get, I guess, very fancy, you could say, therefore, or let's just write it out in words, actually. Therefore, Camille is closer. Oh, I'm sorry. Odette is closer. This is Odette. This is the football. And this is the distance. So Odette is closer, let's say, than Camille. Okay. Not too bad so far. Camille runs along the semicircular path. So here he is. To pick up the football, calculate the distance that Camille runs. Okay, I'm going to erase some of this. Actually, to be honest, yeah, it's going to look messy. So I'm going to actually erase. To be honest, actually, none of this is particularly relevant in the second part. So let's go ahead and work through this. Okay, the distance that Camille runs. So here's Camille. He's going to run and get the football. Interesting. It's interesting that Camille would run for it even though he's further away. Potentially that's meant to throw you off and have you guess that Camille is closer because he's running towards it. Calculate the distance that Camille runs. Alright, 3-mark question. So far this question I think is okay so far. So we want to find this arc. Let's use a new color, let's use blue. So we want to find the length of this arc length right here. And this is semicircular, so what is our arc length formula? This is given in our formula booklet again. Arc length is equal to, we know the circumference of a circle is equal to 2 pi r. That would be one whole, essentially the perimeter of a circle, or the circumference of a circle. But if we don't have a whole circle and we just sweep through a part of a circle, let's say if you have a circle like this, and you just sweep through, let's say, a part of it, then you only have a section. And so the question is, okay, well, what fraction out of 360 do you have? And so we add this to our arc length formula. So theta over 360 times 2 pi r. That is our formula. theta over 360 times 2 pi r. So what is the angle that we are concerned with for this portion of a circle that we have? Well, if this is 45 degrees, and we know angles on a line sum to 180 degrees, we're asking the question, well, 45 plus what is equal to 180, or what is the remainder when we take away 45 from 180 and we have 135 degrees. For a 3-mark question, they would likely want to see that, and given that you're writing in a booklet for this, it wouldn't be enough just to write it on the diagram. So for a 3-mark question, you're going to want to show this. You're going to want to show that simple process. Alright, so 135 over 360, 2 pi, and our radius in this case is 12. Right? This is 12, this is 12. The radius of our circle, distance from the center to the edge, is going to be equal to 12. Alright, let's go ahead. I'm actually just going to work that out on, I don't know, we'll go back to the calculator and work this out. Okay, here we are. Let's go and get a fraction. 135 over 360, and then we're going to multiply this by 2, and pi, which I seem to have forgotten where it is. There it is. 2 pi, and then our radius is equal to 12. Alright. The distance that Camille runs is 28.2743. So let's write that down. Going back to the document. 28.2743 to 3 sig figs. 28.3. In this case, it's meters. Alright, not a bad first question. I don't think, potentially. Alright. Moving on. 15-mark question number 2. Dana makes pendulums to sell at a market. She plans to make 10 pendulums on the first day, 10 pendulums on the first day, and on each subsequent day, make 6 more than she did the day before. So 6 more than the day before. Okay. Part A asks us to calculate the number of pendulums she would make on the 12th day. So if we have this situation where on a certain number of days, or let's say day 1, 2, 3, she's making a certain number of pendulums. On day 1 she makes 10 pendulums, and then on the second day she makes 6 more. So we're adding 6 each time. And she would make 16, and then she would make 22, and so on, and so on, and so on. So what we have, if we're adding a constant, or a set amount, that as we go along, in this case for each day, then we have an arithmetic sequence. So we're in the realm of arithmetic sequences. This is given to you in the formula booklet as well. So let's go ahead. Is there enough room down here? Let's write it up here for now, I suppose. In the formula booklet, under sequences, we're going to have un is equal to u1, the first term, plus n, this is our term number, n minus 1 times d, the common difference. Un is the value of a given term. This is the first term, this is the term number, and this is our common difference. So un, let's get a formula. I suppose, to be honest, I mean, we could just count to the 12th day and say, how many hops do we need to go? Well, it's 9 more days, and she's making 6 a day, 6 times 9, and we could add 54 to 22 to get that value. If we wanted to, for a 3-mark question, would this be okay? Sometimes I actually want to see the pattern rule. That is to say, I want to see you set it up like this. So you can use these kind of intuition and general strategies, but sometimes, according to the mark scheme at least, they want to see something set up like this. Alright, so u1, value of the first term, this is for making 10 pendulums on the first day. N is, actually, let's write a formula, and then we'll use the formula. Actually, no, let's write it out right from the very beginning, because that should be okay. So we want to find the 12th day right here. So U12 is what we want to find. The value of the 12th term. We know the first term itself is 10. The number of terms, we want to find the 12th term, 12 minus 1, and the common difference in this case, how many new pendulums is she making each day, and that would be 6. So the value of the 12th term is equal to 11 times 6 plus 10, and this would give us 76. And I guess, just maybe trivia, 22 plus 54 is equal to 76 that we would have had, I suppose, that way. But this is often a way that the IB mark scheme would, I guess, like to see things presented. You can use intuition, though. Just be mindful of method marks. Okay, number of pendulums she would make on the 12th day, 76. Okay. Part B, she plans to make pendulums for a total of 15 days in preparation for going to the market. Calculate the total number of pendulums she would have available at the market. So now we're talking about the total, and it's over 15 days in preparation for going to the market. Calculate the total number of pendulums. All right, so this is a sum of a sequence, which we actually call a series. It's actually not too bad of a formula, I guess. Let's go and look at the formula booklet. Here we go. This is in our functions, I believe, number and algebra. 1.2, the sum of n terms of an arithmetic sequence. 1.2, right at the top. And we have 2. We have the sum of n terms is n over 2, 2u1 plus n minus 1d. Or we can, the second one right here is if we have, here we go. Whoops, I don't want that. If we know the nth term, if we know that final term, then this is often a helpful way to go about things. All right, but let's use, let's use this one right here. This n over 2, 2u1, n minus 1 times d. Okay. Okay. So let's write that formula out. The sum of n terms, this is for part B right here. Sum of n terms is equal to n over 2 times 2 times the first term plus n minus 1 times d. So it might look a little intimidating, actually, on second thought, but let's unpack it. So the sum of the first 15 terms. So n is equal to 15. Wherever we see n, we essentially can interchange it. So 15 over 2, n is equal to 15, we want 15 terms, 2 times u1. u1 is the number of pendulums that she made on the very first day, which was 10. Plus n, again, is 15, number of terms, 15 minus 1, and then times d. d is the common difference, and in this case it was 6 more each day right here again. And then let's close the brackets. Okay, so S15 is equal to, let's go ahead and type this in on the calculator. Okay. Let's go and get a new calculator screen at very least. Okay. Here we are. 15 over 2. 15 over 2 times, going to need a few brackets, times 2 times 10. 2 times 10, so be careful with your brackets actually in this case. 2 times 10 plus 15 minus 1 times 6. And then we want to make sure that we're multiplying this 15 by 2, or this 7.5, by everything, not just this first portion. So to be absolutely safe, you might even want to work this inner part out and then multiply everything by 15 over 2. So here we go. She is making 234. 234. And I guess maybe it doesn't need to be mentioned, but if you get a decimal or fraction here, something has obviously gone wrong because we're dealing just with whole numbers. All right, 15 over 2 plus 6. So it actually looks like, as I've worked this out, this 15 over 2 times 2 times 10 plus, it looks like this hasn't actually gone as it should. So let's go ahead and work with this again and make sure that it is multiplying everything here. There we go. Okay, so just looking at this as the calculator gives it, we see order of operations, we've just multiplied this, and then we've had this multiplied by itself. But our formula tells us we want to take n, total number of terms, over 2 times this whole business right here. All right, let's go back to the document. 780 pendulums. Okay, let's move on. Dana would like to have at least 1,000 pendulums available to sell at the market, and therefore decides to increase her production. She still plans to make 10 pendulums on the first day, but on each subsequent day, she will make X more than she did before. Given that she will still make pendulums for a total of 15 days, calculate the minimum integer value of X, so whole number value, required for her to reach her target. So integer means no decimals, no fractions, just whole numbers, positive or negative. In this case, it's going to be positive. Okay, so this is C. Let's write it over here. We still have a sum. She wants to make 1,000 pendulums. So we know that S15, the sum after 15 days, is going to be equal to 1,000. And if we're just looking at this formula once again, this one right here, the question is, do we have all the elements? We know n, it's 15. We know the first term. We know the number of days, but this is what we're trying to solve for. We don't know the common difference, how many more she should make each day. She currently makes 6 more. How many more should make? 7, 8, 9, 10? This is the question. She wants to reach 1,000. So let's go ahead and use this formula and put in our new unknowns. So the new sum is going to be 1,000. That's how many she wants. It's still over 15 days, so we're still going to have 15 over 2. And opening up a bracket, we have 2 times U1 is her still making 10 pendulums on the first day, plus n is still going to be 15. She's still doing it over 15 days. And the common difference is what we're trying to solve for. So let's write D. Okay. Again, we could work this out algebraically, but what we can also do is, that didn't work. This is what I was trying to do. We can also n-solve this. So we can also put this into our calculator and n-solve for D. So let's go ahead and do that. So going back to the calculator screen here. Menu, algebra, numerical solve, and let's put in our value. 1,000 is equal to, we can write it as 15 over 2 or a fraction, 7.5. 15 over 2, I'm going to simplify things a little, just for clarity. 2 times 10 is going to give us 20, plus, and 15 minus 1 is going to give us 14d. This makes it a little clearer in terms of dealing with brackets. Tell the calculator what you're solving for, and then let's put in a value. Okay, or let's ask for the value in this case. So she needs to make 8.09524 pendulums. Let's go ahead and go back to the document and write this in. So D is equal to 8.09524, so on, so on, so on. Or we might think, okay, to 3 sig figs, 8.1 pendulums. But it says here integer values, and even if it didn't say integer values, if she's making less than 8.1 pendulums, she's not reaching her target. Only when she makes 8.1 pendulums And we can ask the question, okay, is it possible to make a tenth of a pendulum a day? What would that mean? What does that look like? Here they're laying it out pretty clearly. Only integer values. 8, she's not making her target of 1,000. It's only when she makes 9 pendulums a day that she's reaching her target. All right. Okay. Dana tests one of her pendulums. She releases a ball at the end of the pendulum to swing freely. The point at which she releases it is shown as the initial position on the left side of the following diagram. So this is her releasing it. Dana begins recording the distances traveled by the ball after it has reached its extreme position. So she lets it go, and then only when it's on its way back does she start recording the distance that it swings through or that it travels. And this is represented by the right-hand side of the diagram. So she lets it go, it comes back, and she measures this distance, and then it comes back, and it goes this distance, 16.245, and so on, and then so on, and so on, and so on. All right. So again, some kind of like intuition, common structure that we see. Like the IB is testing a kind of range of skills. It started off with an arithmetic sequence question, and then a sum of a sequence, and then we have solving for an unknown in a sum of a sequence, and now we've got what looks like a geometric sequence. So we're still within that realm of sequences and series. In this case, it's geometric. All right. So here we go. Question 2 continued. On each successive swing, the distance that the ball traveled was 95% of its previous distance. During the first swing that Dana recorded, the ball traveled a distance of 17.1 centimeters. During the second swing she recorded, it traveled a distance of 16.245. Calculate the distance the ball traveled during the 5th recorded swing. Alright, so let's see what's going on here. So it's probably a little larger than we need. So this is n, the number of swings, and then we can call this as un, or we can call it as d, the distance that this pendulum travels. So this is the first, second, third, and we know the first time it was 17.1, the second time it was 16.245, and they're telling us that each time this ball goes from its, let's say, one position back to another, so from, let's say, here and then swinging back to here, it's 95% of what it was before. It's right here. So in this case, we're not adding a constant, we're multiplying by 95%, or 0.95, and then the next distance as well is going to be by 0.95 and times 0.95, and the pendulum swings, the distance that it travels is less and less and less, and we're multiplying this time to go from one term to the next, and that makes it a geometric sequence. Okay. So, calculate the distance that the ball traveled during the 5th recorded swing. 3-mark question. We could just keep multiplying until we get to term number 5, but it's likely that we'll need to use the formula later on. And it's always possible that in some cases the IB is actually looking for the use of a formula. Half interested in actually looking at the mark scheme for this. You can skip ahead if this is, I guess, trivia for you and maybe somewhat irrelevant, but let's check it out. I think this is it, May 2023. Okay. Quick substitution. Recognizing geometric sequence. Okay. A1 is actually a use of a formula. So in this case, it actually looks like they are expecting a formula. So this is part D right here. So let's go back to the document. So we know we have a geometric sequence. We can find the formula for a geometric sequence in the formula booklet, but it looks like this. So the value of the nth term is equal to the first term times the common ratio, in this case what we're multiplying by, or in all cases what we multiply by to go from one term to the next, and then raise this to the power of n minus 1. What does that say? It says how many times are we multiplying by our common ratio. How many times are we multiplying this first term by our common ratio? In this case, we want to find the distance the ball traveled on the fifth recorded swing. So we want to find u5. u1 is the distance traveled on the first time, 17.1. Our common ratio is 0.95. And n, the number of swings, is 5 minus 1. Okay, let's go ahead and work this out on the calculator. Okay, let's get a new screen once again. So 17.1 times 0.95, and we want to raise this to the power of 5 minus 1, or simply 4. There we go. Let's go back to the document. u5 is equal to 13.9281, or u5 is equal to 13.9 in terms of our significant figures, and we can write in centimeters. Alright. Question E. Calculate the distance that the ball traveled during the first 16 recorded swings. Okay, so total distance that this has traveled. This is where we can no longer just use a table and simply add them up, or it's going to take too long for a 2-mark question at the very least. So we're going to need to use a sum of a geometric sequence, or a geometric series in this case. So let's go ahead and look at the formula booklet. Still in topic 1.2, or sorry, 1.3 rather. Here we go, the sum of n terms of a geometric sequence. 1.3, sum of n terms u1 rn minus 1 r minus 1. And we also have this one right here. Both of these are possible. We just see the r is switched around, and if r is less than 1, we could use this formula because it would prevent a negative on the bottom. Not too big a deal either way. So, whoops, let me get back to that one sec. We can use either one. u1, 1 minus rn over 1 minus r. Alright. Okay. So, let's do part E. In this case, we're talking about the sum of n terms, and it's going to be u1, and then we're going to multiply this by 1 minus r to the n over 1 minus r. And that should do it. Okay, so now we have to substitute our values in. Sn, we want to find the sum of the first 16 terms, and it's equal to u1 is the value of that first term is 17.1. 1 minus our common ratio is 0.95. We're raising this to the power of n, and n in this case is 16. Remember, these are going to be the same. Over 1 minus 0.95. Kind of an intimidating looking formula in some ways, but let's go ahead and type that into the calculator. So 17.1, let's open up some brackets and get a fraction. We have 1 minus 0.95. We want to raise this to the power of 16, and we want to set this to some value, 1 minus 0.95. Okay, 191.477. So let's go back to the document. Sum of the first 16 recorded swings is 191.477, or 191 point, actually no, sorry, to 3 sig figs, this is actually just going to be 191 centimeters. Okay. Alright, calculate the total distance the ball traveled during the first 16 recorded swings. Looks good. F. Calculate the distance that the ball traveled before Dana started recording. That's interesting. Okay. Let's actually make use of this table. I'm going to copy it and put it here and just modify it just slightly. Okay. So, so we know this was the first swing. And this is n, and this is un, or simply the distance that it's traveled. And we said earlier that we're multiplying by 0.95 to go from one term to the next. And so the question is, well, what is the 0th? Just like for our arithmetic sequences, if we have n and un, and this was that first situation with, I think it was Dana again. Let's say 0, 1, 2, 3, she's making 10, and then 16 and 22, and we add 6. If we want to go back and find out, I mean, this doesn't make sense in this context, how many she made on the 0th day, but we would do the opposite. We would subtract by 6, and then she would have a value of 4. In the same way here, we are multiplying by some value to go from one term to the next. If we wanted to draw it back, we could take this value of 17.1 and divide by 0.95. And that would be one way. Another way to possibly do it is to set up an algebraic equation. So if we say that this value right here is x, the distance on that first swing, we know x, we know that x times 0.95 gave us that value of 17.1. So that first swing, we don't know what it was, but we know it lost 5% of its kind of total distance. We multiplied it by 0.95, and then it became 17.1. And so this works out to be the exact same of 17.1 divided by 0.95. So I'm actually just going to work that out on my calculator here. Divided by 0.95, and it gives us a clean value, actually, of 18. Okay, 18 centimeters. Calculate the distance that the ball traveled before Dana started recording. 18 centimeters. All right, let's go on to question 3. 15-mark question. A scientist is conducting an experiment on the growth of a certain species of bacteria. The population of bacteria P can be modeled by the function, so population as a function of time is equal to 12,000 times k to the power of t, where t is greater than 0. That means that time is only starting at 0 and greater than 0. Can't go negative. T is the number of hours since the experiment began. So number of hours before the experiment began. And k is some positive constant. Okay. Write down the value of P0. P0, P is our function. 0 is actually just our input. The question is, really, how many bacteria were there when we started this experiment, when we pressed that timer, when T was equal to 0? Let's go ahead and just work it out. A1, let's put in a value of P0, and we have 12,000 times k to the 0, and this of course is just going to be anything raised to the power just becomes 1, so 12,000 times 1 just gives us 12,000. Interpret what this value means in context. Guess we just kind of talked about that. This is the initial number of bacteria in the experiment. Let's just write initial number of bacteria. Okay, not too bad. 3 hours after the experiment began, the population of the bacteria is 18,750. Find the value of k. Okay, so looking back at this initial equation, we have the number of bacteria, P, population of bacteria. We have K, some constant that we don't know, but they're asking us to find. And then T is the time. And here they're giving us a value. When T is equal to 3, P is equal to 18,750. So we have 2 out of these 3 unknowns. We know the population, we know the time, k is the only thing we don't know. So we know 2 out of 3 unknowns. We can set up an equation, essentially just n solve this. So let's go to B. Let's rewrite this equation up here. So we have the population, which is, I'm going to give myself a little bit of room, 18,750, and this equals to 1,200 times k, which we don't know, but we know it's raised to the power of 3. And now we should be able to solve this. You can solve this algebraically, or to be honest, I mean, this is a little repetitive in some sense. You can also n solve. Okay, if you want to solve this algebraically, divide both sides by 1200 and then take the cube root, and you're there. That's actually what I'm going to do here. 18,750 divided by 1200, and then let's take the cube root. Okay, so k is equal to 2.5. K is equal to 2.5. Okay, and you can n solve that, and you should get the same result. Find the population 1 hour and 30 minutes after the experiment began. Okay, C. So we've got this equation. Now it's all complete. We have P of t is equal to 1200 times 2.5, and then we have t. After you've done enough of these questions, you almost start to see where the marks are coming from, and where they're not trying to trick you, but the skill that they're kind of drawing on. So values of t take integer values. So t can be like 1 hour, t can be 2 hours, and so on. But if we have, let's say, 1.5 hours, it's not going to be 1.3. It's going to be t is equal to 1.5. So in this case, we have a function which relates the time to the population, but we're going to need to convert this 1 hour and 30 minutes to 1.5. So let's go ahead and do that. Population at a given time, in this case population after 1.5 hours, is equal to 1200 times 2.5 raised to the power of 1.5. Okay, let's go and type this in on the calculator. Gonna get a new screen. 1200 times 2.5 raised to the power of 1.5. 1 hour and 30 minutes. Okay, so there we go. P 1.5. So let's go back to the document. P 1.5 is equal to 4,743.42. Find the population of bacteria. In this case, to 3 sig figs, this would be 4,740 bacteria. Okay, and that would be our population. Is there anything else to mention? I guess potentially there could be a real-world context question, and they're saying, what is the value of this in a real-world context? This is our initial value. That's what we said right here. It's our initial value, the number of bacteria. This 2.5 is our growth rate, and it's telling us that after every hour we have 2.5 times as many bacteria as we had in the previous hour. So every hour our bacteria not just doubles, but it becomes 2.5 times larger. That's what that would be. Okay. The scientist doesn't get a name. The scientist conducts a second experiment with a different species of bacteria. The population of this bacteria S can be modeled by the function. S of t is equal to 5,000 times 1.65 t. So there's another experiment going on. The initial value, initial number of bacteria is 5,000, and the growth rate this time is 1.65. So every hour we have 1.65 times as many bacteria, I guess. Where t is the number of hours since both experiments began. T, number of hours since both experiments began. So we have two experiments starting at the same time. Find the value of t when the two populations of bacteria are equal. So let's go and write d right here. We have this original population. We have this function of p of t. And let's go back. 12,000 times 2.5 t. This was 12,000 times 2.5 to the t. And this other experiment, s of t, is equal to 5,000 times 1.65 to the t. We see one of them, this one right here, has a higher starting value, but a slower growth rate. So eventually this one with a lower starting point but higher growth rate is going to pass it by. The question that we're asking is, when does pt equal to s of t? When does one population equal the other? Essentially we can set up an equation of 12,000 times 2.5 to the power of t. When does this equal to 5,000 times 1.65 to the t? And should be able to simply end solve this for t. Sometimes exponential equations don't actually work too well. So let's go to the calculator and type this in. So it's possible we may need to graph this, but let's actually just see. Algebra, numerical solve. 12,000 times 2.5 raise this to the power of t. And we want this to be equal to 5,000 times, in this case, 1.65 to the power of t, and solving for t. In this case, it worked out okay. So there it is. After 3.43 hours, or thereabouts, the populations are equal. So let's write that up. T is equal to 3.43. Okay. Good. Let's keep going. It takes 2 hours and m minutes for the number of bacteria in the second experiment to reach 19,000. So 2 hours and some number of minutes, m minutes, for the number of bacteria in the second experiment to reach 19,000. Find the value of m, giving your answer as an integer value. So again, whole number, no fractions, no decimals. Okay, 4-mark question, which, to be honest, sometimes says, so this is going to be challenging, there's a lot going on. But in this case, I think it actually might be a little generous even. So, let's see. First off, let's see. It takes 2 hours and some number of minutes to reach 19,000 for the second experiment. We know we have a function, s of t, which relates the number of bacteria at a given time. So, in this case, we want the sum to be equal to 19,000. And that's the question that we're asking. When does this bacteria population, at what time does it reach 19,000? So let's go ahead and type this into the calculator. This is actually going to be a logarithm if we want to do it algebraically. So let's actually just end solve this. We might need to graph it because sometimes exponentials are tricky, but let's see. Okay, get a new screen. So let's go menu, algebra, numerical solve. We want 19,000 and our starting value was 15,000. This is times 1.65 raised to the power of t, and let's ask the calculator to solve for t. Okay, so it went okay. And thankfully it's roughly 2 hours and so, slightly above 2 hours. So we have something to work with. 2.66587. So let's go back to the document. T is equal to 2.66587. So it takes 2 hours and m minutes, some number of minutes. So this 2 right here corresponds to the 2 hours. So we have 2 hours right here, but plus 0.66587 hours. Essentially, we can write it like that. And the question is, well, okay, like, how long is this in minutes? And if we know that there are 60 minutes obviously in 1 hour, what fraction of, let's say, this 60 minutes do we have? So how can we write this? 60 minutes in 1 hour, we have 0.6658 of an hour. That is to say, we have 0.6658 of 60 minutes. Let's go ahead and work that out. I'm just going to do it on my little calculator, or my calculator right here. 0.66587. And what does that equal to? That equals to 39.952. Okay, find the value of m, the number of minutes, giving your answer as an integer value. Integer, they don't want any decimals or whole numbers. So let's read the question just to make sure, because it is 4 marks. It takes 2 hours and some number of minutes in the second experiment to reach 19,000. Find the value of m, 2 hours and m minutes. Give your answer as an integer value. So it takes 39.952 minutes. As an integer value, 39 minutes, it hasn't yet quite reached 19,000. It's not until, oops, keep the colors the same, it's not until we've reached 40 minutes, 2 hours and 40 minutes, that we have 19,000 bacteria. Okay, kind of generous, I think, at least potentially. Okay, I think this final question actually may be a little more challenging than that previous one, for fewer marks. Okay, final question of part 3. The bacteria in the second experiment are growing inside a container. The scientist models the volume of each bacterium, so a single bacteria, in the second experiment to be 1 times 10 to the negative 18 meters cubed. So this is the volume of one bacteria. And the available volume inside the container is 2.1 times 10 to the negative 5 meters cubed. Determine how long it will take for the bacteria to fill the container. So here we are on part F. What is going on here? So we have some kind of container. Let's just say here it is, something like this. So we've got some container, and there's some little bacteria. Let's just say this. And one of these individual bacteria has a volume of 1 times 10 to the negative 18 meters cubed. And the question is, if we know the growth rate of this bacteria population, which is given by S of t right here, this is the population of bacteria, can be modeled by this function right here. If we know a growth rate for the total number of bacteria, and we know essentially the size of one bacteria, how long will it take to fill up a container that is itself 2.1 times 10 to the negative 5 cubic meters in overall volume? Okay, so let's go ahead and let's try to convert this equation right here, this S of t equation, into not just number of bacteria, but the volume of the bacteria. So overall volume of the population is going to be the population times the volume of the individual bacterium. So if we know the size of one, and we know how many there are, we know the total size, essentially. So let's write an equation for a volume of the bacteria as a function of time. Volume is going to be number of bacteria multiplied by the volume of an individual bacterium. Volume of one bacterium. Okay, so the number of bacteria is given by our equation of 5,000 times 1.65 to the power of t, and the volume of one of our bacterium is 1 times 10 to the negative 18. 1 times 10 to the negative 18. Okay, so this is the overall volume of our bacterium. That's how much size they're going to take up as a function of time. And the question is, okay, well, how long will it take until they fill up the capacity of this petri dish or the container? And that is given by 2.1 times 10 to the negative 5. There we go. Okay, so we've got an equation. We've got the volume of the container. This is the number of bacteria times the volume or the size of one of the bacterium. It gives us the total volume. We want to say what value of t, will make this this equation or this function will complete the function. What value of t will make this true? Okay, let's go type this in on a calculator. So here we go. This is actually going to be, we could graph this, but hopefully NSolve will work. This is the NSolve paper. 2.1 times, oops, that is, something went wrong there. 2.1 times 10 to the negative 5 is equal to 5,000 times 1.65 raised to the power of t. And we're going to want to multiply this. Since we're multiplying, we don't really need these brackets. Multiplication is what's called commutative, so the order doesn't exactly matter. 5,000 times 1.65 times 1. We can switch all these values around and it shouldn't matter at all. Times 10 to the negative 18. Okay, let's check that that is correct. 2.1 times 10 to the negative 5, 5,000. Looks good. And telling the calculator what to solve for t, and it worked. Okay, great. Let's, this value is 44.248. So t is equal to 44.248 or 44.2, was it hours or days? Hours, okay. 44.2 hours. 3-mark question, always in the back of my mind. The question is, do they want us to write this out in minutes? I don't think so. If they did, it would be 44 hours and then 2/10 of 60 minutes. So 0.2 times 60 would be 2 hours and 12 minutes. But then again, it's 0.252481, so we'd probably want to, if we wanted to, which is potentially a big if, 0.2481 times 60, which would actually be closer to 15 minutes. But if this is a scientific experiment and they're going for precision of some kind, this should be fine. I'd almost even caution against this, especially if it's not asked for. Okay. Not a bad question. Determine how long it would take for the bacteria to fill the container. It's good. Okay, question 4. 17 marks. It is claimed that a new remedy cures 82% of the patients with a particular medical problem. This remedy is to be used by 115 patients, and it assumed that 82% claim is true. It assumed that the 82% claim is true. Okay, so we've got some kind of medicine or some kind of remedy, and it cures 82% of patients with some problem. The remedy is to be used by 115 patients, and it's assumed that this is true, so they're not. It's not a false claim. Find the probability that exactly 90 of these patients will be cured. Okay, so we've got this probability situation. and it doesn't look like it's a set of independent events. We can't use a Venn diagram. 115 patients, can't use a tree diagram. So the question is, we've got some kind of distribution, and it's either a normal distribution or a binomial. Normal distribution, they often tell us, almost always, they'll say blank is normally distributed. It follows a normal distribution with a mean of blank and standard deviation of blank. Here we have a set number of trials in this case, or in this case 115 patients. 82%, the success across trials remains constant. So for one patient and the next, the chance of being cured is 82%. And in this case we have a binomial. It's some kind of binary event. We either have a patient being cured or not cured. We have this probability of success. So in this case we're in the realm of binomial distribution. So 4a, let's give it a try. Find the probability that exactly 90 of these patients will be cured. So for binomial distribution, we would want the number of trials. We wouldn't really need to write this. You can write this in calculator notation as binomial PDF or CDF. Number of trials, number of successes, and we also want probability of success. If we have that, we can create our binomial distribution. So let's go ahead and do that and go into the calculator. Menu, let's get a new screen once again. Menu, probability, distributions, and we're in the realm of binomial. Since we just have one value, we can use BinomdPdf, just as a kind of word of caution. NormCdf, NormPdf, just don't confuse the NormPdf and NormCdf with a BinomPdf and binomial CDF. We can't actually use this normal PDF. We don't use it. So sometimes I would almost recommend just use CDF all the time and set your lower and upper bound to the same. Actually, that's what I'm going to do this time, to be honest. Number of trials. Number of trials, we have 115 patients. The probability of success is someone being cured, and that happens 82% of the time. And we want to find the probability that exactly 90 patients will be cured. So in this case, we can set lower bound, upper bound equal to 90. Same thing, probability distributions. Binomial PDF, number of trials is again 115. Probability of success, and then we have 90 patients. And it'll work out the same. Just be cautious if you're using this for NormPdf. We don't use NormPdf. Okay. So let's go ahead and work this out. So there's our probability, 0.0535. All right. So let's write this out. Going back to the document, let's write binom. Let's write binom CDF. I'm going to stick to CDF just because I think it's safer. 115, number of trials, probability of success, and then lower bound, upper bound, and this is equal to 0.0535, or roughly 5%. Roughly 5.35%. You can leave it as a decimal and that should be fine. Alright. Question B. Find the probability that at least 95 of these patients will be cured. B. Again, number of trials, probability of success. Let's go ahead and actually just go right to the calculator screen. So menu, probability, distributions. This one we're going to need to use CDF. Number of trials, there are 115 patients. Probability of being cured is 0.82. The lower bound, we want at least 95 patients to be cured. And the upper bound, potentially all 115. So it says at least, it's including 95. Alright, the chance that at least 95 patients would be cured is equal to 0.491. So let's write that out. BinomCdf, and this is equal to 115, 0.82 and then we have a lower bound of 95 and an upper bound of 115. And that is equal to 0.491, or roughly 49%. And that actually might be helpful. 49.1%. Okay. Part C. Find the variance in the possible number of patients that will be cured. It sounds kind of like an intimidating question, but this is, to be honest, actually not entirely an interesting question because it's just extracting from the formula booklet. So the variance is given to us in our formula booklet for binomial distribution. Let's go check it out. Done. Okay. This would be under probability. We're looking for topic 4. And we have, for binomial distributions, we have our variance, right at the bottom, 4.8. Variance of some variable that's binomially distributed, in this case the number of patients that are cured, is equal to n multiplied by p 1 minus p, np 1 minus p. Okay, so variable of some, the variance of some variable that's binomially distributed is n times p 1 minus p. In this case, number of trials is 115. The probability of success, probability of getting someone cured, and then this is 1 minus 0.18. So, or 1 minus 0.82. That is to say, the probability of success and its complement. N is the total number of trials. So let's go work that out. I'm actually just going to type it in here rather than bringing up the calculator screen. 15 times 1 minus 0.82. Okay. Variance is equal to 16.974, or 17.0 to 3 sig figs. Variance, remember, tells you something about the spread of a population. So if we know, let's say, the average, the standard deviation is the square root of our variance. So if we were to take, let's say, the square root of 17, we would have the standard deviation. That's where it is, I suppose, mostly important when we're talking about variance. Okay. The probability that at least n patients will be cured is less than 30%. So the probability that at least n patients will be cured is less than 30%. Find the least value of n. Find the least value of n. So it's kind of an interesting question, and to look for cues of what they're asking, you might say, okay, well, what have we done above that might relate to this? So, what's going on? The probability that at least n patients will be cured is less than 30%. The probability that at least n patients will be cured is less than 30%. I'm actually going to go ahead and draw this normal distribution once again. So the expected number of patients that we would be able to cure, here we are in part D. Yeah, leave that as it is. Move it down just a little. So the number of patients that we would expect to cure, this is the expected value. This is also given in your formula booklet, and this is just number of trials times probability of success. And generally, in kind of plain language, we have 115 patients, and on average 82% of the patients are cured, or an individual has an 82% chance of being cured. We would expect 82% of this population of 115 to be cured, and so we would expect 94.3 patients to be cured. On average, 94.3 patients to be cured. So if we're asked to find the probability that at least n patients will be cured, is less than 30%. What are we asking? So there's an 82% chance that an individual patient is cured, and it's like, okay, well, what's the probability that we cure at least 10 patients? Well, I mean, there's 115 patients, and the chance of a patient being cured is 82%, so this is going to be high. It's going to be quite high that we cure at least, 10 patients. And similarly, like, the expected number is just going to be 94.3. So the chance that we cure, let's say, I don't know, 60 patients is also going to be pretty good. Chances are we're going to have, at least 60 patients, because we expect around 94.3 to be cured on average in some kind of sense. So the probability that at least n patients will be cured is less than 30. So we want to find this point, in a sense almost like an upper bound, where the probability of us curing this many patients is only around 30%. So we've cured like a certain amount. Like, what's that range of patients? You can kind of think about it as like this optimistic situation. So like you're in a boardroom or something like that, and you say optimistically, what is the chance that we're going to cure, let's say, 95, 96, 97, 98, 99 patients, and so on. As you get closer to this 115, you say, oh, it's going to be pretty rare. It's possible, for example, to cure 115 patients, but the chance of that is going to be so small. And so we're asking about this line of this 30% mark. What is this optimistic value that we cure, a certain number of patients? And it's somewhat optimistic because it only happens, let's say, 30% of the time or around that. This question is kind of funny because I don't believe there is a way to do it without a kind of guess and check and, to be honest, a little intuition. So let's go back to the calculator. Here we go. Probability distributions. And let's go to BinomCdf. We have 115 trials. We have a probability of success of 0.82. And we know that the expected number of patients to be cured is 94.3. So let's ask the question, if our lower bound is 95 and our upper bound is 115, what's the chance of us curing between 95 and 115 patients, given we have 115, the probability of success is 0.82. And we see it's okay, well, 49%. I think that's interesting. That's actually what we just worked out before. Okay, so distributions, BinomCdf, again, 115 trials, 0.82, lower bound. Let's ask the question of, okay, what's the chance that we cure 100 patients out of 115? And here it's only 10% chance, so we've overshot the mark. It's a little too optimistic. So it's between 95 and 100. BinomCdf, number of trials again, 115, 0.82. Let's go halfway between, and let's write 98 or 97. 98 should be okay. Lower bound, 98, upper bound, 115. Alright, so potentially we could still do better. Let's see. Probability, distributions. I believe this will probably be the last one. Number of trials, 0.82. Lower bound is, let's say, 97 this time, and the upper bound is 115. Okay, so here we go. If we cure 97 patients to 115, we have a 30.333% chance of this actually occurring. But we're asked to find the probability that at least n patients will be cured is less than 30%. So in this case, still on the calculator screen, it looks like if we cure 97, between 97 and 115, we have slightly over 30% chance of that happening. Curing 98, between 98 and 115 patients, only happens 22% of the time. So this is the value that is less than 30. So let's go ahead and write that out for part E. BinomCdf, and let's write that out. 115, number of trials, 0.82. This is going to be 98 and 115. And then we show that this is equal to 0.22222. And to be honest, for process, just because it is a 3-mark question, we might want to show this as, well, 97, 115, and we can say that this is equal to 0.303, which is too high. So this is the cutoff point right here, and we want to be less than 30, not more. All right. Okay, so we got one more question, I think. Oh, wow. Okay. A clinic is interested to see if the mean recovery of their patients who tried the new remedy is less than that of their patients who continued with an older remedy. So this is actually continued on the next page. If the mean recovery time, the average recovery time of patients who tried the new remedy is less than the patients who tried an older remedy, the clinically randomly selects some of their patients and records their recovery time in days. The results are shown in the table below. So we want to see if the mean recovery of the new remedy is less than that of the old. So let's call new memory, the new remedy, mu1, and let's call old remedy mu2. So the mean of group 1, mean of group 2, the average. The data is assumed to follow a normal distribution, and population variance is the same. What they're saying is that on the calculator you can write pooled is equal to yes. For the two groups, a t-test is used to compare the means of the two groups. So we're using a t-test, and our significance level is 10%. State the null and alternative hypotheses for this test. So we've got our null hypothesis and alternative hypothesis. For t-test, it's always going to be mu1 is equal to mu2, so status quo, no difference in the averages. In this case, how are we relating mu1 and mu2? Mu1 is the new remedy, and we want to see if mean recovery time is less. So once we average all these values here, we want to see if the average recovery time of this group, mu1, is less than mu2. This is actually a pretty important part, because if this is incorrect, then, to be honest, everything else actually will be as well. So make sure to put it into context. We want the new group, the average recovery time, to be less than the average recovery time for the old group. All right. Let's continue. Find the p-value for this test. Okay. This is just us running a t-test. So after that, state the conclusion, give a reason, and explain what the p-value represents. That's interesting. I've never seen that one before. That's nice. Okay, so let's go back to the calculator and work this out. So let's go into spreadsheets. I'm going to get a new window. Spreadsheets. Let's put x and y. And let's put in the values. So these are the values for x. 12, 13, 9, 13, 14, 15, 17. And this is 17, 11, 10, 18, 20, 22, 14, 15, 18. Great. And it doesn't matter that there is a difference here. Okay, we've got our values in. You might want to check, if this is a timed exam, you might want to actually check that you've put them in correctly. And I think these are good as well. Okay, menu, statistics, stat tests, and we want to do a t-test. T-test, whoops, I'm sorry, we want to do a 2-sample t-test. Statistics, stat test, 2-sample t-test, there it is. Alright, list 1 is in our x's, list 2 is y, no frequency. We're asking the question if the average of group 1, the new remedy, is less than group 2, and pooled, this equal variance, and normally distributed would be yes. Okay, group 1 less than group 2, everything's good. There's our p-value, 0.062. Okay, so let's go back to the document here. P-value is equal to 0.062036 figs. G, state the conclusion for this test, give a reason for your answer. So it doesn't ask for context, it just asks for reject the null hypothesis or fail to reject the null hypothesis. So significance level is 10%. Let's write 0.0620 in this case is less than 0.10, or essentially 6.20% is less than 10%. So we would reject the null hypothesis, or you can say reject HO. Reject the null hypothesis. And that is why, because our p-value is less than the critical value, or rather the significance level. Alright, part H, explain what the p-value represents. This is an interesting question. Haven't actually seen something like this before. The p-value represents the chance that we see these results just based on probability alone. So you look at two samples, and what is a possibility that you have this kind of difference between these two populations just based on random sampling alone? In this case it's 6.2%, which is rather small. So I'm just looking right here. The mark scheme has this written. I'll show you actually as well. So the mark scheme says, just going all the way down here, this is what the mark scheme is asking for. The probability of obtaining results at least as extreme as those observed, given that the null hypothesis is true. Yeah, to be honest, I would have written something probability or chance. Probability we see these results from two independent populations, from two independent samples. Results, we see these results by chance alone. You're selecting two independent samples, so just random samples of individuals on the street kind of thing, so long as they're random samples. Selecting two independent samples, results by chance alone is selecting two independent samples. Essentially 6.2% we see these results just based on chance alone. I think what they're saying is the chance that the null hypothesis is true. That's not too bad either. 6.2% chance that the null hypothesis is true. We're saying, hey, we want at least 10% chance if we're going to accept it. Alright, last one. Let's see what we can do. A particular park consists of a rectangular garden of area 8 meters squared and a concrete path surrounding it. The park has a total area of 1,200 meters squared. The width of the path at the north and south side of the park is 2 meters. The width of the path at the west and east side of the park is 1.5 meters. So here we have 2 meters, the width of the path, and here's the width of the path on the east and the west side, so east and west side. The length of the park along the north and south side is x meters, and x is greater than 3 and less than 300. So we know it's larger than 3 meters and less than 300. So we've narrowed it down somewhat, I guess. So just to summarize this question, we've got this park, and we're going to put a path around this garden. The width of the path on this, let's say, north and south edge is 2, and the width of the path on this east and west edge is 1.5. I'm going to put a path in this part around this garden. Write down the length of the garden in terms of x. Okay. So the length of the garden, this is going to be the length of the garden. And we want to write this in terms of x. So L is equal to, so we know that this right here is the total length of the garden, right? This extends all the way to x. But it's not exactly equivalent to x because we're missing this part right here, this 1.5 meters, and we're also missing this 1.5 meters. So the length of the garden is not equivalent to what x is, but it's less 1.5 times 1.5 or less 3 meters. So, or you can write x minus 2 times 1.5. So it doesn't stretch the whole way. It's 1.5 meters less on this side, 1.5 meters less on that side. So length is equal to x minus 3. Find an expression for the width of the garden in terms of x. This is kind of an interesting question. So we want to find an expression for the width of the garden right here in terms of x. So to do this, let's look at the values that they've given us. They've told us that the area is equal to 1,200 square meters, and by and large we haven't yet made use of that information. So let's see what we can do. Just as a kind of aside, the IB will rarely throw in information that isn't useful. They might tell you that, you know, a Toyota is from 1953, or something like that, but by and large, in a geometry question where you're given, let's say, area, likely, if we haven't yet made use of it, chances are we will in some kind of sense. So, write down an expression for the width of the garden in terms of x. So what do we know? Area itself is equal to length times width. In this case, let's say the area of the park is equal to the length of the park times the width of the park. If we can find the width of the park, then we can find the width of the garden, because we know that the width of the garden is just 2 less and 2 less than the width of the park, or 4 less than the width of the park. So let's see if we can find the width of the park here. Area is equal to 1,200. The length of the park is equal to x, and the width of the park is equal to WP. So we've now got an equation of WP in terms of x. So we've got an equation WP in terms of x. How do we get this by itself? I'm just going to rearrange this. X WP, width of the park, is equal to 1,200. And what we can do is we can divide both sides by x, and essentially we have width of the park is equal to 1,200 over x. So I ran out of space a little. Width of the park is equal to 1,200 over x. Okay, and if the width of the park, I'm actually just going to bring this down here. Sorry, this is a little cluttered. If the width of the park and the width of the garden, we're asking how are these related? The width of the garden is equal to the width of the park, but less than 4 meters. This is 2 meters right here. This is 2 meters right here. If we're just asking what is the difference between the width of the garden and the width of the park, the width of the garden is equal to the width of the park, but minus 4 meters. And now here's where it becomes, a little challenging, is our algebra. We're saying that the width of the park is equal to 1,200 over x. This equals is the same as saying is. Width of the park is 1,200 over x. So what we can do is we can say that the width of the garden is equal to, and then substitute. These things are interchangeable. And there it is. That's our width of the garden, 1,200 over x minus 4. Find an expression for the width of the garden in terms of x. Here it is. Hence, show that the area at A is equal to 1,212 minus 4x minus 3,600 over x. A is the area of A, and a concrete path surrounding it. This is a rectangular garden of area A. Okay, so when we're talking about the area A, we're talking about the area of the park. This is okay. This was the area of the park. This A is the area garden. So area P is the area of the park. Area A is just the area of our garden. Okay, so we know that the area, this is part 3. Let's write it over here. Part 3, we know that area is equal to length times width for a rectangle or square, for example. So what is the length of our garden? The length of our garden is given by x. And the width of our garden is 1200 over x minus 4. Okay. So, is that all we need to do? No, it can't be. Okay. My mistake. The width of the garden is not equal to x. The width of the garden is x minus 3. I thought that looked a little funny. So, let's move this just over just slightly. Okay. So the width of our garden is actually x minus 3. And here we have it. And now, this is going to be quite challenging. They're asking us to do some expansion. So again, we have a binomial. That means to say 2 terms. So 1, 2 terms. And to what extent, this is going to be a method mark. So that's already something. What we need to do if we want to write this equation as a is equal to 1212 minus 4x, and so on, is we're going to need to expand, multiply each of the terms by each other. When we do that, we'll get something like this. A is equal to x times 1200 over x, x times negative 4x, negative 3 times 1200 is going to be negative 3600 over x, and negative 3 times negative 4 is 12. So, simplifying a little more, let's put our 1212, grouping just our constants. This negative 4x is the same, and we have 3600 over x. And thankfully they match up. Alright, find the possible dimensions of the park if the area of the garden is 800 meters squared. Okay. Find the possible dimensions of the park if the area of the garden is equal to 800 meters squared. So it's interesting. We have area of the park and we have area of the garden. So we have this formula for the area of the garden, and here it is. I'm actually going to copy this. I hope I can copy this. Let's see. Okay, looks good. So we have a formula for the area of our garden, and we know that the area of the garden is equal to 800. So let's go ahead and substitute to find the value of x. Is that all they're asking? Find the possible dimensions of the park if the area of the garden. Show that A refers to a rectangular garden. This is the area of the garden. The rectangular garden is given by A. This is an equation relating A as a function of x. Find the possible dimensions of the park. Okay, so let's substitute 800 into here. 800 is equal to 1212 minus 4x minus 3600 over x. Okay, now we may need to graph this just because it's rational and it's 4 marks. So let's see if we can end solve this first off. Okay, let's go ahead and see if we can end solve this. It seems a little too straightforward, I feel, for a 2-mark question, or 4-mark question rather. Minus 4x minus 3600 over x, solve for x. Okay, 9.64. X is equal to 9.64. Okay. X is equal to 9.64. In the back of my mind, I'm wondering if, because this is a rational equation, there aren't, let's say, two solutions. There aren't, let's say, two solutions where this thing could potentially be 800, but I believe it should be one. I believe it should be just one solution. If you wanted to, should we graph it? Should we graph it? Should we graph it? Okay, I'll graph it real quick. Feel free to skip ahead. 1212 minus 4x minus, let's write this out as 3600 over x. Let's zoom fit. Okay, there's our function. And if we add another graph of 800, let's zoom in on some area. Where are we now? Window zoom. Zoom in. This is a rather strange cursor. Okay. Okay. So I believe 1212 minus 4x minus 3600 over x. We wanted to see when this was equal to 800. And it was at 9.64. Sorry, I wonder if this is a little tedious. Let's go negative 10 to 10. That should be fine, because if it's at 9, let's go 15. And y min, I don't know if we need it that high. It should only need to be at about 1,000. So let's go maybe 3,000 just to make sure. And we can call this negative 100. And there's our intersection. And we do only have one. We do only have one intersection. Okay. So there it is. Not bad to confirm, especially if you can do it quickly. 9.64. That's our value for x. Okay. So let's go back to the document for a sec. Find the possible dimensions of the park if the area of the garden is 800 meters. So x is 9.64. That would be our length. And the width, the park has a total area of 1,200. So once again, area of the park is equal to the length of the park times the width of the park. X itself is the width of the park. Or sorry, the length of the park rather. And so the area was 1,200. Wait a sec. The area of the garden is 800, right? So the area of the park is 1,200. The length of the park is 9.64. And the width of the park is what we're trying to solve for. Kind of a funny question. To be honest, I think it's almost in terms of juggling these values. Okay. Area is equal to length times width. Minus 4x minus 3,600 over x. And we said the area of the garden is 800. Okay. The area of the garden is 800. Alright. And so we know that x itself is 9.64. This is 1,200. The funny thing is, if we work this out and divide both sides by 9.64, we get 124.5, which I don't know if that's just meant to confuse us. So let's go back to this sketch. I see. Haha. Okay, there it is. Analyze graph. intersection 93.4. Wow, geez. So that's a final question on paper 2. So going back to the document for a sec, when they say find the possible dimensions, it's possible that we have 2 solutions. So we do actually have 2 solutions. X could also be equal to 93.4. So this is one pairing. If x is equal to 96.4, that is to say the length of the park is equal to 96.4, the width could be equal to 124.5. If x is equal to 93.5, then again we have the situation where the area of the park is equal to 1200. In this case, our length is 93.4. What's the width of the park? Dividing both sides by 93.4 divided by 93.4, we have the width of the park is equal to 12.847 or 12.8. So what do we have? This is a possible dimension, length and width, and we can put length of the park, width of the park if we want it. 93.4 or 12.8, or potentially we can have a situation where we have 9.64 and 124.5. So these are 2 possible sets of dimensions. Okay, getting there. Find an expression for the area or the derivative of this area function right here. So let's go down. Part C, only on part C so far. If area is given by 1212 minus 4x minus 3600 over x, they're asking us to find the derivative. So this is like if you have like y is equal to, let's say, 5x squared plus 3, and they're asking you to find y prime, which is equivalent to dy dx. They're asking you to find the derivative. So let's go ahead and find dA dx, which we could also essentially call a prime. Alright, to first do this, actually, since we have something in the denominator, a variable in the denominator, we're going to want to rewrite this. So let's write this as area is equal to 1212 minus 4x, and whenever we have something in the denominator, we need to, not something, but a variable in the denominator, we need to write this out as a negative exponent. So 1 over x is equal to x to the negative 1. 1 over x squared is equal to x to the negative 2, or 1 over x to anything is equal to x to the power of negative n. And it doesn't really matter if we have suddenly, like, let's say 6 over x squared. That's the equivalent of 6 times 1 over x squared, which would be 6 times x to the negative 2. Let's use that same idea to convert this. This will be negative 3600, and then we'll have x to the negative 1. And now we should be able to use the power rule. So this is a little more challenging, and this is kind of deliberate, I think. They put the constant at front. Usually the constant is at the end, and we know we can just remove it if we're taking a derivative. In this case, we remove the constant when we take the derivative, so this first term is actually just going to go away. If we have negative 4x, it's the same as x to the negative 1. X just falls away, so we have negative 4. You can think of this as negative 4x to the 1. We take the derivative, it's negative 4. Multiply out in front, x to the 0. Anything to the 0 is just 1. So we have negative 4. And then we have this value, which will be the most challenging, this third term. Negative 1, multiply out in front. Negative times a negative leads to a positive. So we're now at positive 3600. It was negative 1, and now it's going to be negative 2. So remember, in your formula booklet, we have the derivative, which is given by, I'll write it out here. If we have some function f of x is equal to x to the n, when we take the derivative, we're multiplying this exponent out in front, and then we're reducing it by 1. That's exactly what we did here. We had -1, multiplied it out in front, and then we reduced it by 1. So there it is. There's our derivative. Use your answer from part C to find the value of x that will maximize the area of the garden. Alright, so to be honest, the easiest thing would actually be just to graph the area of the garden right here and then find its maximum. And to be honest, that will almost certainly give you one mark just for the answer. But they want you to use your answer from part C. They want you to use the derivative. So here's a conceptual kind of explanation of what they're asking you to do. So if we have some situation, for example, and let's even draw the graph, or at least this portion that we had that was relevant. We saw it like went, what did it do? It went down, and then it went up. Actually, no, I think it was in the negative portion where it went down. So let's deal with just this positive portion here. And so we had this graph, and it went, and then it started going down again. And we had this point where the area was maximized. And if, let's say, our derivative, which it is, our derivative is a tangent at any given point. So if we wanted to, let's say, find the slope of a line, I'm actually going to write this with a little bit more of a slope. So let's say, for example, our function looked like this, which it kind of does. This is area as a function of x. At any given point, we can find the slope of a tangent line. Right here it's increasing, here it's still increasing. But there's going to be a point where we're going to have no increase at all, where it's going to be flat. And that's going to be the point where our derivative is equal to 0. Our derivative looks at the slope of a slope of a function at a given point. And so we want to ask the question, okay, well, when is the slope equal to 0? When is it done increasing? Before it starts decreasing, it's going to have a point where it's exactly flat, where the slope is equal to 0. And so what they're asking you to do is set this equation. So this is part D. They're asking you to do for this is to set the derivative equal to 0. And I'm just looking at this now. I forgot a variable. They're asking you to set this derivative equal to 0 and then solve. And we can do that. And you can actually just end solve this, and it should be fine. So what I'm going to actually do here is I'm going to look at the original function. So going to the calculator, I'm going to zoom out, and I'm going to take a kind of cheat step, because this is what they're asking you for. They're saying, okay, can you set the derivative to 0? And we can end solve that and find the value for x. But if we already have a graph of our area against the size of x, let's go ahead and find its maximum. Find the maximum of this one, the area. And it happens when x is equal to 30. So when x is equal to 30, we have an area of 972. Okay. The other option, so we're back in the document screen, is to essentially, end solve this function right here. Just end solve for x. And that would be the point where we have a slope of 0. All right, find the maximum possible area of the garden. Okay, this is a 2-mark question. Find the value of x that will maximize area of garden. It's interesting because the questions are very similar. So when x is equal to 30, for part E, we know that the area. This is what we found on the previous screen, just going back to it right here. We found the maximum when we looked at our original function, this blue function right here. We found the maximum earlier on. So we found that maximum, this point right here, where we reached the highest point. When x is equal to 30, we have an area of 972. So let's go back to the document. Area equals 972. It's a 2-mark question, so they would, at very least, an examiner would want to see a sketch. So let's go ahead and just roughly approximate this. So here we go. Is our asymptote close to 0? Maybe rewrite that just a little, make it a little closer to 0. So we've got this function, and it approximates, has this asymptote at 0, and then it comes down from the negative, and then it goes down once again. And this was our maximum, and it occurred when we have x is equal to 30 and y is equal to 972. And that should be enough for our process. Not needed, but we have area as a function of x, the size of the path. And so when or sorry, not the size of the path, the dimensions of our garden. I'm sorry, not our garden, our park. Okay. All right, everybody. Not a bad exam. I think the questions were fair. Overall, quite good, I think. All right, I think that's about it. I hope it was helpful, and I wish you the best of luck. Okay, bye-bye.